Hello everyone, and welcome to today's chem lesson. Today we're going to talk a little bit about isotopes and what it means when first we say the word isotope, and how we can look at the different isotopes of a given element and get the average atomic mass, the number that shows up on the periodic table for that element. Now, we spent some time in our last video looking at examples of elements. Right? We had all of our fancy numbers in our bottom left, and upper right corners. We talked about how this number in the bottom left is the atomic number, and that's equal to the number of protons. This number up here in the upper left corner is the mass number, and that's equal to the sum of the protons and the neutrons. And how this number in the upper right corner is the charge, and how that is the protons minus the electrons. Now, we're going to ignore charge. We're going to focus in on atomic number and mass number today. The same element, right, meaning the same atomic number, can have different mass numbers. You can have different atoms of the same element with different numbers of neutrons. Because if they have the same atomic number, then the only thing that changes is this number of neutrons. And when we look at different copies of the same element that have different numbers of neutrons, those are isotopes. Right? An isotope is when you have the same element. Right? So same number of protons, but different mass numbers. Right, so different numbers of neutrons. And this now leads to an interesting dilemma. If this leftmost calcium has a mass of 42, and this rightmost calcium has a mass of 44, and this middle calcium has a mass of 40, when I look at the calcium box on the periodic table, what number should I put for the mass? Should I put 42? Should I put 40? Should I put 44? And the answer to that question is we're actually going to just average together our three different masses, or all of the different possible masses. Right? That's why when you looked at the numbers on the periodic table, they're often decimals. Right? These mass numbers, or atomic masses I should say, are averages of all of the naturally occurring isotopes. So if we take a closer look, let's look at something like carbon 12, 13, and 14. Right. Yeah, actually, that's not a good enough line. Let's go carbon, carbon, carbon. Carbon is always atomic number 6. Let's look at carbon 12, carbon 13, and carbon 14. Like I said before, we know that they are the same element because they have the same symbol and the same number of protons, the same atomic number. Right, so all of these things have 6 protons. When we look at the neutrons now, this first one has 6, right? 6 plus 6 is 12. 6 plus 7 gives us our 13. And 6 plus 8 gives us 14. So these are isotopes of each other. And if we want to know what numbers should be placed in the atomic or periodic table box for carbon, we are gonna average together these isotopes. And we're going to talk about how to do that in a second. But first, a practice problem. Which pair here is a pair of isotopes? So here, if we're looking for a pair of isotopes, we want the same element but different mass numbers. The only one that satisfies that condition is 2. Right. Choice 3 and choice 4 just shows the same atom. Right? Those aren't isotopes, those are just duplicates of the same exact atom. And here we have 2 different elements, right? We're going to have 2 different atomic numbers. Right? And that doesn't make them isotopes, that makes them 2 different elements. Right? They got to have the same atomic number, right? Be the same element but different mass numbers. Now let's talk about that averaging. Like we said, we got carbon 12, carbon 13, carbon 14, right? Different types of carbon. Big C, little 14. Right? Each one of these isotopes of carbon is going to contribute to the number that goes in the periodic table. It's going to contribute to the average atomic mass. But we're not just going to add these 3 things up and divide by 3. We're not just taking an average of the options. We're taking a weighted average. So we want to look at how common each of these things is. All right, we want to take a look. Which one of these is the most abundant? Which one of these is the least abundant? So for example, right, and these are not numbers that are accurate. Right, we'll say 95, 1, and 4% of all carbon. Right, 95% of all carbon is carbon 12. 1% of all carbon is carbon 13. 4% of all carbon is carbon 14. So we're not just going to say 12 plus 13 plus 14 divided by 3, because that would give us 13. We're going to average, taking into account the abundance, the percent of each isotope. And there's 2 different ways we can set this up. We can set this up as the mass times the abundance for each combination, and then divide that whole thing by 100. That will take into account that there's a lot more carbon 12 than anything else. Or, equally as mathematically viable, we can do the decimal version of these percentages and not divide them by 100. Right? Either one of these mathematical setups will get you the same answer. All right, these 2 things are going to be equal, right, when you solve it out. But you can take mass times the abundance as a percentage and then divide the whole thing by 100, or mass times the decimal version of the abundance, and then you don't have to divide the whole thing by 100. This is essentially the same way that your grades get calculated. Right? If you have 10 quizzes and you get 150 and 9 100s. Actually, for the sake of my writing, let's make it 5 quizzes. Your average isn't a 75. Right? You don't just take the 50 and the 100, add them together, divide by 2. Right? You're going to take into account the fact that you got a bunch of other high grades. Your grade is going to be a lot closer to 100 than it's going to be to 50. And that same thing is going to hold true here. When I look at these, this number is going to be much closer to 12 than it's going to be to 13 or 14, right? It'll be to 0.011, right? It'll be a small boost above 12, but it'll be very, very close to 12 because 95% of the numbers you're averaging together are this 12 number. Right, let's take a look at some examples. Here I've got 2 different problems, and I want you to take a minute and try to set up, right? You don't have to plug in, you don't have to solve, just set up the correct math for these 2 problems. Use the exact weight and the abundance. When I want to solve this out, I'm going to take my exact weight times the abundance. I've got 2 options. I can take exact weight times the abundance as a percentage, for each of my options. And then divide the whole thing by 100. Or I can take those same numbers, that exact mass, and this time instead of multiplying it by the percentage, I can make that percentage into a decimal, right? By moving the decimal point over twice. Right, 9890, and then do the same thing for the other side. Now remember, to convert a percentage into a decimal, you have to move the decimal point over twice. So I took this decimal, I moved it over twice, and then I moved it over twice again to get those numbers. And in this case, I do not need to divide by 100. Right? I already did my division by 100 by moving the decimal point over twice. I get the same options in this second problem. Right, where I can take my exact weight times the abundance for each thing, adding them together and then dividing by 100. Or I can do that exact same thing, but make those percentages into decimals. Right, moving the decimal point over twice. Be careful when you're moving the decimal point over for small percentages. It's easy to mess that up and get the wrong number to plug in. Here, we're moving it twice, so we should have 0.0037. Right, and again, either one of these options is totally fine. Let's look at one more set of practice problems. This time I am not going to color code. Again, 1 minute on the clock here to do your best to set up, not solve, just set up these problems. Thank you for telling me. Right. Either option is totally valid. Right. You can take your exact weight times your abundance as a percentage as given, or your exact weight times the decimal point version of your percentages. We're going to see that again here as we look at 27.97697 times 92.23. We're going to do this for each of the three. Right? It's always been 2 up until now. Now we're looking at a third. It doesn't change the setup other than adding that last term. of space. And then divide the whole thing by 100. And again, or you can do this exact same setup, but take your percentages and turn them into decimals. Now, if we look at this mathematical setup, before plugging into the calculator, we can actually tell where this number should be. We know it has to be between our lowest and our highest, so it's got to be somewhere between 27.976927, right, but less than 29.973770. We see that there's a 92% abundance of this lower one, which means my number is going to be very close to this bottom limit, right? If I'm averaging together 27.9, 28.9, 29.9, but there's 92 copies of 27.9, then my average is not going to go very high. It's going to stay near this lower boundary. And so without even plugging into the calculator, just by looking at the data you're given, you can actually get a good estimate of where you're supposed to be. So if you plug this into the calculator and it comes out as 52, you know that you've made some mistake somewhere. Right? You can always look at this and think about where your number should be and see if the number that you get matches, right? If you plug this in, you get 28.01. That seems pretty good, right? It's a little higher than your 27, right? Pulled up a little bit, but not that much, right? It's within the range of what it should be, right? Higher than your lowest and lower than your highest, right? But, all right, 52.68 means you messed up something in there. There's a decimal point in the wrong spot. To wrap us up for today, let's try one more multiple choice problem. We're taking the atomic mass. What are we averaging? The most common isotope, the least common isotope, all of the naturally occurring isotopes, or the radioactive isotopes? Here, our correct answer is actually choice 3. When we are averaging these things together, we're not just taking whichever one is the most common. We're not taking whichever one is the least common. We're taking all of the ones that had occurred naturally, right? When we think back to how this affects, when we looked at the comparison to grades, if I've got 150 and 4 hundreds, your average is not 100. Your average is not a 50, right? It's not just the one you got the most of. It's not the one you got the least of. It's the naturally occurring grades that are being averaged, right? All of the ones that exist. And with that, I'm going to transition us over to our Zoom meeting for questions, comments, concerns, and attendance. And I will see you there.